Hello Gators, we're going to do 4.6 approximating values of a function using local linearity and linearization. All right, let's take a look at this curve. This curve is called concave up. And think of concave up as something that can hold water. So something that can hold water. Concave down, think of something that spills water. All right, so that's how I'm going to explain concave up and concave down. Now, I want you also to take a look at this tangent line. This tangent line and that I'm going to call L of x, L standing for linear. So L of x is this tangent line and this is f of x. And I want you to notice at the point of tangency, they're exactly alike. If we're really close to this point of tangency, the line and the function really are close in y value. So over here, this y value and this y value are very close to each other. The farther you go out, this y value and this y value are not so close. But as long as you're close to the point of tangency, the f of x is approximately L of x, as long as you are close to the point of tangency. Now let's look at this next diagram. This next diagram is concave down, and I want you to notice that again this is the tangent line. We say it's L of x, and this is f of x. And these two functions are very close. Their y values are very close to each other as long as you are close to the point of tangency. You get too far away from that point of tangency and these y values are very much separated. But as long as they're very close to the point of tangency, the y value of the line and the y value of the function are very close to each other. Keep this in mind. All right, so let's go ahead and write an equation of a tangent line for this. Here's the curve and here's the tangent line. So I'm going to take the derivative to find the slope. I'm going to evaluate it at 1 and I have the slope. And then I use point slope form, and then I solve for y. And the reason I'm solving for y is because I want you to understand this y is a line. So I'm going to write line, and this is going to be -3 times x minus 1 plus 3. So I have found the equation of the tangent line. I'm going to use the tangent line equation to approximate f of 1.1. So the linearization is approximately the function as long as I'm close to x equal to 1. All right, so we want to use the linearization, the line, and we're going to put 1.1 into the line, and this will be -3 times 1.1 minus 1 plus 3. And this answer is -3 times 0.1 plus 3. So this is -0.3 plus 3, which is 2.7. So we use the line to approximate f of x. Now, if we actually put 1.1 into the function, we'll look at what we get, 2.669. So you can see that these two are very close to each other. And this is a great approximation for the actual value. All right, let's go ahead and take a look at this curve. The curve is concave up. I've kind of drew it concave up. And we know that the x value is 4, the y value is 5, and we know the slope of the tangent line right here is 3. So we would like to use the line to estimate the value of the function at 3.8. So the equation of the line is going to be y take away 5 equals 3, that's our slope, x minus 4. And I'm going to call this y my linearization. It's a line, and then I'm going to move the 5 to the other side. So it'll be 3x minus 4 minus 5. So I now have the equation of the line. Right here, I already have it there. I guess I don't have to write that down. So I have the equation of the line, and I'm going to use, and I know that the linearization the line is approximately the function when it's close to 4. As long as it's close to 4, this is a pretty good approximation. So I'll do the linearization, and it's going to be at the number 3.8. 3.8 is definitely close to 4. And I'm going to put it into this a formula that's really nice. 3, and then I'm going to write 3.8 minus 4 minus 5. Okay, now this is going to be a negative 0.2, so this will be negative 0.6 minus 5, and so that the answer is going to be negative 5.6. So this y value right here at 3.8, the y value on the line is negative 5.6, and that is going to be a very good approximation for f of 3.8 will be approximately negative 5.6. These two values right here are very close to each other. Now, is this an underestimate or an overestimate? Now, since the line is sitting under the curve, because this is concave up, then we say that the negative 5.6 is an underestimate because the actual value is a little bit higher since the tangent line is sitting underneath the curve. All right, let's take a look at this function, and we see it's they're telling us it's concave down at x equal to 1, and we want to find the tangent line at x equal to 1. So at x equal to 1, I really do need to know my y value, and my y value will be 5, take away 2, minus 2, so the y value will be 1. That is necessary. And I'm going to need to find my derivative to figure out my slope. So that'll be 5, take away 6x squared, and so the derivative at 1 will be 5, take away 6, which is negative 1. So my tangent line will be y minus 1 is equal to negative 1 times x minus 1. I'm going to call this L of x, and then I'm going to move, this is negative x minus 1 plus 1. So this is my linearization, this is my line, my tangent line. Here's my function, and I'm going to use this line because I know the linearization is approximately the function when x is close to the tangent line, which is x equal to 1. So as long as it's close to x equal to 1, these are very similar. So we're going to do B part. I'm going to use the linearization 1.1. So I know my f of 1.1 is approximately the linearization, and I'm going to put 1.1 into my formula, negative 1.1 minus 1 plus 1, and that's going to be negative 0.1 plus 1, which is actually 0.9. All right, now, so my y value right here at 1.1, the value was 0.9. Now, since the tangent line is above the curve, because this is concave down, it's above the curve, we say that 0.9 is an overestimate because it is concave down. Concave down means the tangent lines are sitting above the function, not below. All right, consider this differential equation. So they've already given us the derivative, and they're telling us that the point is 2, 0, and they would like us to figure out the equation of the tangent line. So this is already a slope, so I'm just going to put, wherever I see a y, I'm going to put a 0, and everywhere I see I put an x, I'm going to put 2. Everywhere I see a y, 0, everywhere I see an x, I'm going to put 2. E to the 0 is 1. This is going to be 8, take away 10, so the answer is negative 2. That will be the slope of the line. So now I can write y minus 0 is equal to negative 2 times x minus 2. I'm going to take my L, I'm going to call it L of x because it's the tangent line, and I'm going to ignore that 0, so it'll be negative 2 times x minus 2. And I know that the linearization is approximately the value of the function close to x equal to 2. All right, now they want me to use the tangent line to approximate f of 2.2. So f of 2.2 is approximately L of 2.2, and I'm going to use my equation, my linear equation. I'm going to put 2.2 in for x, and then this is going to be negative 2 times 0.2, and so the answer is negative 0.4. And negative 0.4 is the approximate value. I don't have to say overestimate or underestimate because I really don't know what the concavity is. All right, can we approximate root 26 using the equation of the tangent line? So here's our function, and we want to write the equation of the tangent line, so I've got to find the derivative, and the derivative will be 1 over 2 root x. And the number I'm going to use as the point of tangency will be 25. 25 is close to the number 26, and 25, it will make my substitution process very easy. So this is 1/10. All right, so the slope of the tangent line is 1/10. So it'll be y take away 5 equals 1/10 times x minus 25. And again, my y, I'm going to call it L of x, and it stands for the tangent line, and that's going to be 1/10 of x minus 25 plus 5. So I know my linearization is approximately my function close to x equal to 25. So I'm going to approximate f of 26 by, and that'll be approximately the linearization at 26. And when I put 26 in here, I will have 1/10 times 26 minus 25 plus 5. So this answer is 1.1 plus 5. And so the answer is 5.1, which seems very reasonable. Root 26 should be a little bit more than 5. And this is the end of the screencast.